So 2D matrix we have been given and we need to find out the kth smallest element. So online tutorials suggested one approach was a heap based approach. Okay, we have been given just briefing out the question, but I'll suggest that you come here after reviewing the question and after reviewing the solutions as well from other YouTubers, because I'll be brief. I'll only tell the optimal solution and will focus mostly on the intuition behind that solution. So yes, so first approach is heap based approaches that in this sorted matrix we have been given, this is sorted, this is sorted, right? Row is sorted, column is sorted. So let us say let us take an example, kind of example. So okay, 1 8 10, fine, 4 9 15, 5 14 17. The motive behind taking my example right now is that I want to take the maximum distance between some any two elements or something like that. Okay, maximum distance, I mean like the gap between a few, like two elements, has to be greater, much greater, so that I can conclude my point appropriately. So heap based approach uh, tells us that we have to find out the kth smallest. So take a heap of k size and keep adding elements into the heap, each element, and keep removing the elements from the top of the heap uh, to have the kth element at the last. So how would that work? We will be basically taking a max heap so that we can keep removing the maximum elements we get as we iterate over the array, and whatever is left at last will be the maximum element in k size starting from 0. So like that concludes kth smallest. That will be the thing. This is explained by the YouTubers. Now let's come to optimized solution explained by them, which was kind of a binary search solution. So what they were saying is, not what they were saying, I'll just tell the optimal solution, the intuition behind this. So basically in this matrix we know that 0 comma 0 is smallest. Okay, so this is smallest and this is largest. 0 comma 0 is smallest and n minus 1 and m minus 1 is largest, right? This is largest, m and n being m being the row length and n being the column length, 3 comma 3 in this scenario. So yes, we know these two things. So the algorithm is that we basically we take put start as 1, we put end as 17, and we basically check the mid. And what do? Ignore these arrows for now. We have the mid now, right? From mid, the thing is that we will basically count number of elements smaller than my mid. Getting my point? Just example, 1 in 17's mid is 9. So in this matrix we will count all those elements which are smaller than 9, right? How many are smaller than 9? And please note, in this question the matrix can have repeated elements. So our approach will handle that thing too. We'll tell the intuition as well. Okay, Let me just write repetitive. I have to explain repetitive how my algorithm is also handling this case. So we need to find out all those elements that are smaller than mid. Why? Now let us see the intuition as well. Then I will continue this. Intuition is, let us visualize this matrix in form of linear array, sorted array. 1 4 5 8 9 10 14 15 and 17. Okay, this is linear representation of this array. So idea has come when the person visualized the 2D matrix in form of linear sorted array. Only after that they were able to visualize that okay, we can do binary search. How? We found we set these two as start and mid, right? Start and mid. We find out the middle, which was 9 currently, right? And we see that how many elements are smaller than 9 currently. Let us suppose our k was 6. We have to find out the sixth element, which is 10. Okay, 10 is the sixth smallest. 1 2 3 4 5 6. So 9 is currently mid. How many are smaller? 1 2 3 4. 4 elements are smaller than 9. Okay, 4 elements are smaller than 9. And how much elements we want, which has to be smaller than our mid? Basically, suppose if our mid was 10, then how many smaller elements has to be there? 1 2 3 4 5, right? Basically we want 5 smaller elements. Like whatever is our mid, it the smaller elements, count of smaller elements which are smaller than our mid has to be 5. Only then our answer will be appropriate. Getting my point? So only if our mid is 10, only then we will have 1 2 3 4 5 5 elements smaller. Okay, so currently our element smaller than mid is 1 2 3 4, which is not fine. We need to increase our mid so that our element smaller than mid increases as well. So let us increase our mid. From 9 it becomes 10. Now how many elements are smaller than mid? 1 2 3 4 5. Okay, 5 are smaller and 5 we want. But shall we return the answer now? No, not at all. Why? Because let us suppose if instead of 10 it uh, it was 11. Got it? It was 11. Now what would have been the answer? The answer have been 11. But when we were at 9 we saw that okay, this is 4. Sorry, smaller elements count as 4. So we try to increase the start. How we increase the start? Always in binary search we write no start equals to mid plus 1. So start becomes 10 now. 9 plus 1 is 10, right? 9 plus 1 is 10. So start would have been here. Basically start would have been here somewhere at this place here, right? Now start would have been here and is here itself, and is here. So that's why is at 10 now. When start is at 10, then we saw that basically we found the middle of 10 and 17. It would have been 13. 13. Okay, 13 is somewhere here. So finding out for 13, we checked how many are smaller count. 1, 2, 3, 4, 5, 6. 6 smaller. Okay, this is larger. We want, right, we want 5 smaller, but this is 6. So what would we'll do? We decrease the end to mid minus 1. So now mid becomes 13 minus 1, which is 12, and start is 10 itself. What is the middle of 10 and 12? It's 11. Okay, so 11. So basically 11, when we got 11, we saw that okay, 1, 2, 3, 4, 5. Count is 5, which is apt for us. So when we found the apt count, we still do not stop. We put start equals to mid plus 1. Okay, so start equals to 11 plus 1, which is 12, and end is 12 as well. And now we check the mid is 12. What is the count of for the mid? 1, 2, 3, 4, 5, 6. 6, which is not what we want. So we move end to 12 minus 1. 12 minus 1 is 11. Now what is the count? Before checking the count, we see, oh, this is our base case reached. The while loop terminates because end is now smaller than start. So we return end. We return end. Okay, this is answer, which is 11. Got it. What's the intuition? I have explained the dry run actually. So what's the intuition behind this? That we do simple binary search. We check both start and end. uh, Start and ends mid we check, and we check if the count we want is exact that particular frequency we want. Okay, if it is, then we increase start, and if it is not, then we check if it is smaller, then we increase start. If it is greater, we decrease end to mid minus 1. What it does is that basically it makes sure that whatever the point when start and end overlaps and extends each other, which is our base condition. When this happens, then at that point the the end element is always the one which is present into the matrix. It took me almost 2 days to develop the intuition that why is it so that whenever the loop terminates, always the element on which it is terminating is present in set. How is it happening that it is always present in set? Then finally I like developed this algorithm as well. On online there is kind of a different algorithm which they are not checking the smaller elements, they are checking the k and so on, but this seemed simplified to me. I shall tell you what is happening here is why the point where start and end overlaps and extends to the opposite direction, at that point end is the one which is present into the matrix. This is happening because suppose mid is here, okay, and the element which is our answer is here. Okay, suppose there were 3 elements present here and mid comes to be here. Okay, suppose it was start, it was end. There are few elements present here as well. Suppose anything, but this is the main point that mid comes here, and this is our answer that we want. Now mid is here. If we would have returned mid, right, if we would have returned mid, then it would have been wrong. Why? Because this is not even an element in our matrix. Our element is this. So that's why we still keep moving our start to mid plus 1. Now why we are moving to mid plus 1 and not mid? To basically avoid the base condition, like infinite loop. How? Suppose start was end was 17, start was 16. Suppose this. Okay. What's the mid? Mid is 16. Okay. 16, and it fulfills the condition we want. So we assign start as 16. Then in the next loop, start is 16, end is 17, mid is 16. Okay, it fulfills the condition. We assign start is 16. In the next loop, start is 16, end is 17. You see, it's causing an infinite loop and not getting out of the loop. What do we want? That start has to extend the 16 to 17, and that's when we check that 17 is increasing in count. We want count n, and 17's count is n plus 1. That's when we assign end as 16, and that's when we terminate the loop. Okay, so this is the intuition behind why we are assigning start equals to mid plus 1 and not mid. Okay, got it. Coming to here as well. Okay, so start became mid plus 1, as I have explained in the tuition. Okay, so start is here now, and reminding you this is our answer which we want, and start is here now. End is here. In the next iteration, their middle comes out to be somewhere here, and we see that okay, this is increasing in count, so we assign this as end minus 1, like end assign end as mid minus 1. So end comes here now. Okay, we check it's mid, it comes out to be here somewhere. We again check, okay, this is increasing in count. Okay, so you will assign end here. Now their mid comes out to be this. Got it? This, which is our answer. Now we check, is it appropriate what we want? Yes, it is. Okay, whenever something is appropriate, we assign it as start? No, we assign start equals to mid plus 1 always. We assign start equals to mid plus 1. Why? Because of this example. Got it? So we assign start as here. So start and mid are pointing to same element here, and this element doesn't even exist in matrix. What exists is this one. Okay, so this is not still our base condition. Our base condition was always that while start is smaller than equal to end, and it is equal to end. Okay, so it is the base condition is not hit right now, it is fulfilling the base condition right now. So we continue. As we continue, we check that okay, this it their mid comes out to be this as only, and it is increasing in count what we want. So what do we do when increases? We decrease the end to mid minus 1. So mid end becomes this, and when it becomes this, we see okay, uh, this is not satisfying our base condition. So base condition is not satisfied, so we goes out of the loop and returns end, return end, and this is our answer. Got it? I will be attaching the code, my and kind of comments are there just for the ease of understanding. LeetCode link, you can refer there for the code. I just gave you the intuition, and specifically intuition behind why the point when start and end are overlapping and extending each other and coming out of the loop. Why at that point our end is always present into the matrix, because this was the only doubt which made me spend 2 days on this question just for figuring out why it is happening, and I was not able to figure out with the solution present or online provided via Claude AI, or even like solution forums of Lead Code or the YouTubers. So I kind of made my own solution. Just kind of similar, but it's more understandable towards the intuition we have to develop. So I hope you got my point. And again, explaining it very last, that why they are overlapping, because we are not stopping at the point where our mid gets satisfied. We are always suppose our mid is here at where my red pen is, and these are start and end. So when mid is satisfying, we are always putting start after mid, and after mid, if it is still uh, satisfying, that means our mid was never the one which is present in set, which is present in matrix. So this is totally fine. Now our mid becomes here, and now we see that okay, this is something which is not don't which is increasing in count. So we always decrease the into mid minus 1. So mid comes so now start and ends mid comes here, and this is the answer actually. So now we see okay, this is satisfying condition. So as always, we brings start to mid plus 1, and they are overlapping now, start and end. And now as they're overlapping, the mid also comes here, which is not an answer. And when we count its count, we see okay, this is not our answer. So we basically decrease the end to mid minus 1, which was, and our conditions are for loop, while loop breaks, and we return end, and end is our answer, because we this was the answer always. Getting my point? Also, a small intuition point at last, if someone is confused, that why are we basically, why is this working? Because in our array, the count will only becomes differ. The count of smaller elements only differ only when some element is present into our matrix, and we stand after that element, right? Getting my point? Sorry, I'm extending the video, but just have to be clear with the point. If this is our matrix, these are kind of elements 0 1 2, oh sorry, 0 6 11, any element, right? Increasing order, sorted. Yeah, also we'll explain about the duplicates as well in here. So basically, if something count here is fulfilling, right, count here is also fulfilling. Two elements are smaller. At this point also two elements are smaller. At this point also two elements will be smaller. But when we come here, these are fulfilling, but when we come here, their smaller elements become 3. So this becomes invalid. That's when we decrease our pointer to mid minus 1. Getting my point? So count is only getting changed via those elements which are present into our matrix. That's why this solution is working. Talking about the duplicates, so even if it is duplicate, actually if you kind of dry run this code which I'm providing, and after this video you will understand the duplicates point as well, and also will understand this intuition I'm saying. We need to dry run at least 2 times even after my explanation. That's when you would be cleared with the concept. Still will basically tell you the duplicate thing. So suppose 0 1 9 13 13 15, suppose like this, and 13 was our answer. So we like the answer we need is something like 4, right? K is 4. We need to find out the smallest element is 4. So no problem, like whatever our intuition algorithm is, it will cover the duplicates. Like it doesn't get affected by the duplicates. There are no conditions for the duplicates in our algorithm, specifically that duplicates will change. Basically, if start and end is here and mid comes to be 9, okay, 9 is not satisfying, it is smaller, the count is smaller at 9. Okay, we increase the start to somewhat here at this point between 9 and 13, like 10, right? At 10, okay, at 10 the condition is satisfying. Okay, this whenever condition is getting satisfied, it still increase to 11. Okay, uh, like actually not after 10, it the mid note doesn't get 10, the mid gets to be like 10 and 15 would be 12. Okay, so at 12 also the condition was getting satisfied. Okay, whenever condition getting satisfied, we move start to 13. Now 13 and 15, middle is 14, somewhere here 14, and at 14 condition is not getting satisfied, so we move end to 13, which is somewhere here, right? End is initially end was 15, now end is at 13, and start is also at 13. Now you are seeing two 13s, start and end, but in algorithm point of view, it doesn't care about the rank of the elements or the index of the element. As you know, the start is a number, end is a number. We are no more considering start and end as a pointer, unlike every other binary search. So that's why it doesn't matter. Okay, start and end is equal, and it is still fulfilling our condition. So as always, we move start to 14. 13 plus 1 14. Okay, so start becomes 14, start becomes 14, and end was 13, end was 13, start is 14. This just terminates our for while loop because of base condition unsatisfaction, so it returns end, and end is 13. So the point was that duplicate doesn't affect it. Why? Because duplicates, even if there are 10 10 times 13 written in our matrix, why does it matter? Start is 13 and end is 13, and our condition is always, and mid is 13. So like our condition is running on the number, not the indexes. Getting my point? So duplicates doesn't matter. So yeah, I have summarized the intuition as well, and yeah, you can please rewatch the video if needed and try it. It needs one day at least of investment, just question, but it will be a lifetime luxury that you will never forget the intuition. Okay, thank you.